this is visible?
Yes, sir.
So we were using conductivity or the electrical conductivity as the figure of merit for comparing the material performance for making electronic devices. So that was the first thing. And then one thing we might have noticed is the conductivity is a function of all these materials. We have seen three categories of materials: metals, semiconductors, and insulators. Uh, in all these cases, conductivity was changing, or there was a variation in conductivity with the temperature, and then uh, the nature of variation in
Sir,
these three yeah.
sir, PPT is not visible.
Just 1 second. Okay, now.
Yes, yes, sir.
Yes, sir.
Is it okay?
Yes, sir. Yes,
Hello.
sir. Yes, sir.
Yeah. So these were the things we have discussed in the we have seen in the last lecture, that there is a change in the conductivity with the temperature, and the nature of variation in these three categories were different. In one case, we have seen conductivity increases with the temperature. In one and the other case, we have seen a decrease in the conductivity, and our third category was there. There was not much variation in the conductivity with the temperature. Now we need to look into this aspect: what is causing this variation, and why they are different in these three categories of material, and has it got any useful purpose? From this can be infer anything. So we have seen that again we have defined one more thing. Conductivity was discussed in terms of two parameters. One is the carrier concentration. Other one was the mobility. These two parameters we have seen. So any conductivity variation with the temperature has to be seen in the context of variation in the carrier concentration or mobility with the temperature. So we need to keep that thing in mind. Immediately we are not going into that, but that picture should be there, that conductivity depends on two factors: the carrier concentration and the mobility. So any variation with the temperature will be caused by the variation in the carrier concentration and mobility. So that has to be kept in mind. So that we will be taking it after some time only. So, but that picture should not be forgotten. So now let me ask you, when these three categories of material we are considered, is there anything common in them? So we have seen there is a difference in the conductivity, but what are the things in common? Let us see. Have you noticed anything common in them? Anybody? Hello? Hello?
So conductivity is being changed according to different
No, no,
aspects.
my question is there were three categories of material. Is there anything common in these three class of materials? That is a difference, no? Variation in conductivity, that is a difference actually. Now, my question is there anything common in them? Have you noticed something common?
Sir, temperature. Um,
No, because as far as the material is concerned, physical and chemical properties of
Okay, okay.
property, yeah, anything common. Yeah. So you got my question. We have seen there is a difference in their conductivity and the variation of conductivity with the temperature. There is a difference. Now we have to see whether is there any commonality between them or anything common to them. Most of these materials are familiar. You have seen this is aluminum, copper. Then we have seen, I don't have the table with me, but I think you all recollect that silicon, germanium. Then you have the diamond as an insulator. See, we are considering, actually, one thing we have to understand, we are considering here the elemental, like elements only, but there can be insulators, compound or mixture of materials can alloys, for example. Alloys are a mixture. Actually, it is a solid solution, metal solution. They are known as alloys. They can also act as they can show metallic properties. Then there can be polymers, which are having they're like rubber, etc. Uh, they can show excellent insulation, uh, insulating properties. Then semiconductors, compound semiconductors are also there, gallium arsenide, gallium nitride, indium phosphide, etc. But initially, we are focusing our attention to elemental materials like elemental metals like aluminum, copper, then silver, gold, etc. Then semiconductors like silicon, germanium, and then insulators like diamond, things like that. So, what is common in them? That is the question. Yeah. No answer? You have not observed anything common?
So they all are solids.
Pardon?
They all are solids.
Yeah, this is very important observation. All of them are solid. So that we need to keep it in mind. So that is what we are coming to. They are all solid state materials. So, because that's very important, the properties which we are going to discuss, this mostly observed in solid state of the matter. We all understand, right from school days, we talk of this matter can exist in how many states are there for the matter?
So basic three states.
How many?
So three states.
Three states. So, solid, liquid, and gas. So now, what is the physics of solid formation?
So the
Atoms
particles
are
are
Yes, one at a time. Yeah.
atoms are tightly packed.
Yeah, actually, this is that's like if you look into microscopically into these three kinds, because we have seen the matter can exist in solid, liquid, and gaseous form. The important thing is the interatomic space, interatomic distance. So in solids, the interatomic distance is the lowest, and the gas, the interatomic distance are very large. So that is the one important difference we can see between these three states of matter. So what we are talking here is mostly applicable to solid state. In fact, the whole electronics based on these materials are known as solid state electronics, actually. Or so these semiconductor devices are otherwise known as solid state devices, because earlier we had the vacuum tubes. So in order to make a distinction between the vacuum tubes and the semiconductor devices, we very often call semiconductor devices are solid state devices. So there is another physics of semiconductors are very often known as solid state device physics, actually. So this is one important difference. So whatever properties we are talking of hereafter is for the solid state. Actually, that means the interatomic distances are small as compared to the other states of matter. It's all relative again. We can talk of interatomic various solids will have various interatomic distances and all those things. So, but important thing we can see is they are all solid state. Any other thing? All are solids. All of you agree to that? Any other thing? Yeah. So again, there are the solids. See, when you coming back to solids, they can be divided into two categories. One is crystalline solids, and the other one is the amorphous solids. You all understand the meaning of a crystalline solid?
Yes, sir.
Yeah. So this figure may not be big. I picked up one figure, but then may not be very evident. It's a figure may not be showing you clearly the crystalline nature. Crystalline nature means there is a periodicity. The atoms are arranged in a regular fashion. Then we talk of a crystalline material. And amorphous, there is not that kind of any order. Of course, when solid state, since uh, uh, Prashant has brought this question earlier, I would like to mention that there is a different state of solid states also, that is known as the glassy state. So there are glass. So whereas mostly solids can be categorized into crystalline and amorphous. Glasses are mostly amorphous in nature, but then they are very often, strictly speaking, they should be treated as a separate category. But right now we are not going to the glasses because right now our focus is to these two kinds of solids, that is crystalline solids and amorphous solids. Again, we can see that whatever we are talking today, or in the context of this device physics, mostly applicable to crystalline. That means crystalline material. So that means there is a periodicity in their atomic arrangement. So whatever physics we are discussing is applicable to this crystalline material. So that again we can see that whether you talk of metals, whether the semiconductors we have talked of, so that is silicon and germanium or gallium arsenide, then the insulator which I talked of, that is the diamond. These all have, for graphite, of course, I have not mentioned. I talked of as an example of an insulator, I'm taking the diamond. So all these are crystalline in nature. So that is an important thing we have to keep it in mind. So this crystalline materials also, there are two categories. One is because since when you start the course, you will say always crystalline and amorphous. But when you are reaching at the master's level, you should know that crystalline materials are also kind of two kinds. One is monocrystalline, and the other one is polycrystalline. Monocrystallines are sometimes known as simple crystalline only, and there is polycrystalline. Are you familiar with any polycrystalline material? Yeah. Any polycrystalline material?
No, sir.
Anybody? Yeah. Actually, all metals are polycrystalline in nature. Metals are, whereas normally the semiconductors which talk of silicon, germanium, etc., they are monocrystalline. Of course, silicon can be uh, polycrystalline also. Silicon can be amorphous also. There are amorphous silicon. There are a lot of application of amorphous silicon in this display devices, then in solar cells, etc. Amorphous silicon is used. There are polycrystalline silicon is used in your MOS for the gate region, so the gate material. So polycrystalline silicon is also there. So important thing is the periodicity is not that long. Long range periodicity may not be there. So then we talk of polycrystalline materials. But we need to understand that this crystalline materials can be two type. One is monocrystalline, that is one kind of unit cell is repeated, and the other one is a polycrystalline. There is periodicity, unlike amorphous. There will be a periodicity, but unlike crystalline, the periodicity is the unit cell may not be identical and things like that. So metals are the best example of polycrystalline material. Then, but silicon also can be converted into polycrystalline or amorphous. So these crystalline materials can be monocrystalline or polycrystalline. Yeah. So again, we are talking about mostly about crystalline or polycrystalline material. That's also very important. So these are known as the bulk properties. Bulk properties. So that means we are physics. We are trying to understand the physics involved in these materials. So then we talk of bulk means we are considering an infinitum. That means this dimensions x, y, z going. We have shown only the 2-dimension, but we need to consider the 3-dimensional picture of these materials, and they are going to x, y, z direction. They will be going to infinity, because otherwise there is a discontinuity. The physics we develop is going to be applicable for material which is going into infinity in 3 directions. But then later on we see that that is not possible. There will be a finite dimensions involved, so that will introduce changes in the physics actually. So that has to be kept in mind. But right now we are saying that okay, x, y, z directions, these material are going to infinity. So they have a structure there. These different crystalline materials will have different structures. This silicon, germanium, etc. has a diamond-like structure. So that is the parent, like that. Yeah. So now we are see one important thing. See, any semiconductor physics starts with the energy band in solids. Actually, if you look into any book on semiconductor devices, you'll see that it starts with energy bands. So again, you all are familiar with atomic theory, the Bohr atom model, etc. So you know that there is a central nucleus where positive protons and neutrons are there. Then you have, and surrounded by you have electrons orbiting. So you talk of energies levels of the electrons. So there is a atomic model that is it was postulated by Bohr. So it is known as the Bohr atom model. It somewhat resembles the your solar system, but there are differences. So I will not go into those details, but you should be aware that it is not identical. Some similarities are there. That's all. It's not that they are exactly matching. Then the type of interaction and all those things are different. And then if you go further into nucleus, you know that there are further sub particles are also there. Proton can be further divided and things like that. So it goes on and on, like you are peeling off an onion. So that anyway, so we will not go into that. So now the question is, as we have seen, when you are forming this, so what is the difference between energy levels in the atoms and in the solids? That is what we have to see. So when you are bringing atoms close, the close proximity, then these electrons, or naturally the electrons of one atom will be interacting with the atom of the other electrons. So their energy changes, energy level changes. So you have to understand, we are talking of here the potential energy of the electrons. Even though they are orbiting, this energy is due to the position. So as you understand, the positional energy is known as the potential energy. So these are all the potential energies of the electrons which we are talking of, and they are bound to the nucleus because there is a Coulomb interaction between the nucleus and the electrons. So they are bound to the nucleus. So these are the potential energies we are talking of. And when another atom or a nucleus is close by, its energy changes. So when we have two atoms close, then we will see that energy of the individual electrons will be changed, because naturally the Coulomb interaction, that is intuitively you can see that it will be changed. So you will be having very close space to energy level. So in a solid, what happens is you have a large number of atoms. So let us say if n number of atoms are brought, then you have n states will be produced, and then again these are known as the available states for the electron. That means these electrons can occupy these states. That is what we see right from the Bohr atom model. We were seeing that these are the places where the electrons can occupy. So, and again, we have seen that there is something called Pauli's exclusion principle. So, no two states can occupy more than one electron. So, you have each level can have two. There, the spin differences will be there. So that way, each states can be occupied by two electrons, differing in their spin. So you can n states are there, then two n electrons can be accommodated. So you have, when n atoms are brought together, you have two n n number of states and two n electrons can be there. So this is, so you have a continuum of energy states formed. So that is known as, so when you have a continuum of energy states, you talk of energy band. Just like continuum of frequency, you talk of frequency band. There is a group of energies. That is the meaning of band here. So, so this again, it's yeah, like again, it depends on the material. You'll see that these energy levels can be continuum. Then there can be a gap, and then again a continuum. So there can be allowed energies. There can be empty states, empty energy regions. So very often they are known as the forbidden and the forbidden region of energies, and then there can be further energy states and things like that. So that is the kind of thing. See here, one thing important we need to understand, even though we started with that Kelvin statement, that Lord Kelvin's statement that we like quantifying the things are very important. But in this discussion, I will not be going into the quantification of the thing, because actually one can calculate all these energy states, and one can find out the energy. Then you can find out forbidden region. All those things can be, and the different materials. You can find out the energy states, energy band, energy gap, or the forbidden gap, etc. All these things can be calculated, and there are well-defined that. But we will not be going into those things. We will be having a qualitative discussion only. So that, because that itself is like a lot of physics is involved, I don't want to divert there. Like we don't need to go into those details. But then we will not do that. So then, see, so as an analogy, what I will do is I will take a electronic oscillator. Fundamental oscillator is an LC oscillator. You have a this is very often known as a tank circuit. Again, high school or graduate level, you might have studied about LC circuit. I am not shown any resistance here. So these are the basic building block. That is resistance, capacitance, and inductance are the basic building block of a passive electric circuit. But here we are showing only LC. The resistance part is not shown. But we know that an inductance stored energy in the magnet as a magnetic field, and the capacitance as a electron charge. So then like they can work as an oscillator. That is not the point which we are going to discuss here. So each tank circuit has a resonance frequency decided by the value of L and C. Now, when I bring, see, just like that, so you assume that one tank circuit in the left side is one atom. Now, you have two identical tank circuits. You are bringing them close. Then the resonance frequency will be influenced or changed by the mutual induction of the other tank circuit. So there will be a change in the frequency. Just like in the solids, you can bring in. I did not draw that diagram, but one can bring in many tank circuits together from different directions, like in the case of a solid. So all those the mutual inductance will cause a change in the resonance frequency. So you'll have a band of frequencies can be generated, just like energy levels in solid. So this is a good analogy which can be used to understand the energy band formation in a qualitative fashion. not in a quantitative fashion, but in a qualitative fashion. You can understand what is happening within a solid. When you have an atom, you have a discrete energy states. When you have a solid formation, you have energy band formation and things like that. So this is so. In fact, one of the classic work on semiconductor device physics given by William Shockley, that is electrons and holes in semiconductors. He has beautifully described all those things with this analogy, and there he has used a mechanical oscillator. That means a spring and a mass system. So you have used a coupled mechanical oscillator. So since I am not using that, since we are familiar with the LC oscillators, they are identical. So I have brought in the analogy of the LC oscillators. So you can visualize that how energy bands are formed with this picture in mind. So it's kind of so that means essentially the energy states of individual electrons are influenced by the neighboring atoms. So that is what the potential energy is changed by the neighbors. So if n atoms are brought, so they will be having n states and things like that. So one can visualize it like that. Yeah. Any question there?
No, sir.
So here we need to understand that these are only, see, when we are talking about interaction between the neighbors, only the valence electrons come into play because they are because the other one, the innermost shell, valence electrons are the electrons in the outermost shell. So they are the valence electrons because in the chemistry, the exchange of these valence electrons are the whole chemistry is based on that. So we know that all those exchanges and different kinds of bonds formation and ionic bond, covalent bond, and things like that. So where the electron exchange that takes place between the outermost shell electrons. So they are known as valence electrons. So they decide the valency of the element under consideration also. So so valence electrons are the electrons which are taking when we are talking about the energy states, it is the energy states of this valence electrons. And another important thing we need to understand is this energy, it will be decided by the atomic number and the interatomic distance. These are two very important points. That the atomic number and the interatomic distance. Earlier we have seen that interatomic distance, but then the atomic number also will decide the electron energy states. So here I would like, because if we need to go beyond, a lot of things are happening in material engineering, but it may not be very relevant for our immediate discussion, but still I'm giving a bit of elaboration here. So we can play with this actually. We can change the atomic number, the neighbor. See, for example, you have a silicon atom. And if you bring, instead of another silicon atom, we are bringing a germanium atom or a gallium arsenide atom or a molecule very close to that, naturally the energy levels will be changed. Similarly, the distance between the atoms, we can change. So in both these cases, the energy states will be changed. So because as we go further, we see that the energy band uh, structure is the most important thing in semiconductor devices characteristics. So by band gap engineering, if I can change the band gap engineering, band gap according to my application, a lot of things can be done. And in fact, the most of these optoelectronics, you have a paper on optoelectronics, so there you will be studying this importance of this band gap engineering and how the band gap can be changed or controlled as per the application. The basic principle used is simple. Actually, the atomic number and the interatomic distance can be manipulated. You have the technology available. Very often, nanotechnology, that is what we do. So you have what is known as the heterostructures. Like you have neighboring atoms may not be this identical, or even the distance can be manipulated. Then we can have, but nature doesn't permit that. So we have to artificially do that. But we have once we understand this, so the principle used is very simple. You have the atomic number and atomic distances are controlled. So band gap engineering is possible. That is very important today for many of these applications, especially in your optoelectronics applications, like whether it is for semiconductor lasers, which is very often mostly used in your communication application, optical fibers. The backbone of the optical fiber communication is the semiconductor lasers. Then you have LEDs. Again, all kind of applications are there, semiconductor LEDs. Then you have the detectors, photon detectors, etc. So wide variety of applications are there with this band gap engineering. So I wanted to mention it here that now when we look into this, so without any reason, I'm not getting into the reasons here, but if you look into this, you see that these materials show three kinds of band structures. One is a continuum of band structure. Actually, let us start with the insulators. Insulators have, it is observed that there is a continuum of energy. Also, you have a band, and then there is a gap, and then there is again further continuum. So there, so it is going higher in the energy. So you have lower one is known as the valence band, and the upper one is known as the conduction band, and there is a gap in between them. So this is the picture of the insulators and the semiconductors. Also, they are identical. Only thing is the forbidden band or the forbidden gap is small in the case of semiconductors. So that is one thing. And whereas the other one is you have on overlapping. That means only one band of energies you have, or partially filled uh, conduction band. So one thing we need to keep it in mind: all these energy states are formed by valence electrons, but the lower band is very often known as the valence band. The upper band is known as the conduction band.
Sir,
Yeah.
diagram is shown here, sir.
Hey, yes.
Sir, the diagram of valence band is not being shown.
Hello. I didn't get your question.
Sir, diagram show नहीं हो रहा है यहाँ पे.
I am not showing any diagram.
Oh, okay, sir. Okay, sir.
Text. All the text is visible. Hello.
Yes, it is visible.
Yeah. I have not come to the diagram. There is no diagram on this slide.
Okay, sir.
Your voice is not very clear, so try to adjust that. I'm like I had to struggle to. After all, I'm an old man, so you should be, or you speak bit loudly so that I hear. Yeah. So then, so we can see this. Earlier we have seen the conductivity, three types of conductivities. One is increasing with the temperature, decreasing, and constant. So along with this, we see that if you look into the energy band, we see three kinds. One is with a large band gap, one is with a small band gap, and there was no band gap. So metals are typically that. So here I would there's a link shown in the slide. So this slides I will be posting. So already that is posted in the Piazza. I don't know if any of you have noticed that. So there is a beautiful video lecture on origin of energy bands in solids and energy bands in semiconductors. What we have discussed, I have discussed briefly, but more detailed way it is discussed, and I have shown the link, and I have taken the Khan Academy video for that. So have you heard of Khan Academy?
Yes, sir.
Yes, sir.
Yeah, so it will be interesting. I find it in a short 8 minutes video he has explained. Many other things are also discussed. So if any of you are interested, you can, some of the physics concepts, if you are not very clear, you can go. But this particular lecture will be like, it will be more fruitful if you go through these two. One is the origin of energy bands, which we have discussed in briefly. So yes, more elaboration is given. And then energy bands in semiconductors. These two lectures are already I have posted the link, so you don't have to worry about searching and getting it. So it is there in Piazza. One can watch it there. Use the 8 minutes each, I think. Yeah. So this is what Prashant was talking of. So this will give you a clear picture. So as you go in the y-axis, this is the energy. You have the conduction band. Then the upper band is very often known as the conduction, because most of the time the conduction band electrons are taking part in the electric conduction process. So that is why they are known as the conduction band. Valence band, of course, the lower levels are there. All of them are valence electrons only. But still, the upper bands are known as they have more energy. So because as you go in the y-axis, energy is increasing the upward direction. So they have more energy, so they take part in the conduction process. And so in leftmost is the insulators. We have a large band gap, typically around 5 electron volts or so. That is the typical value. Then this if the band gap is below that, this is typically around 5 or below 3, 3.5. Then we talk of semiconductors. You have like element we are like silicon, germanium, etc. And then there is no gap between. Then we have the metals actually. So these are the three categories. So that way you can see that insulators and semiconductors are similar, and with metals, of course, they have a different type of energy band structure. Yeah.
Sir, can you
Yeah.
please explain the conduction
Yeah.
band?
Yeah.
Sir, conduction band, can you explain it?
Pardon.
Sir, I want to know about the conduction band.
Combustion. I didn't get your question.
Sir, please explain conduction band. You
Yeah,
want to
conduction
say?
band. See,
Yes.
actually, there is a continuum of energy bands. So you have a lower levels are known as the valence band. Upper level, the conduction band, they can see they are free to move. Probably in the next slide it will be clear, but still let me see that. So you have this conduction band is not fully filled. So there, the electrons can move. When you apply electric field, the electrons can pick up the energy, then go to different energy levels. So that is why they are known. So that way they can take part in the conduction process. If it is fully conduction band is fully occupied, there is no states available. That doesn't happen normally as far as the conduction band is concerned. So then there cannot be any conduction. Okay, this is very important to understand how the conduction takes place. See, for conduction to take place, when you are applying the energy or giving electric field, carriers need to pick up the energy and they need to move to a different state, a different energy state. If there are no states available, so just like in the valence band, suppose all of the states are filled, that is typically possible in a valence band. So no conduction impossible. So in an insulator, what happens is normally the valence band is fully filled and conduction band is empty, and the gap is very high that it cannot go from valence band to conduction band. So what happens is its conductivity will be very small because few electrons might be there in the conduction band that may take part in the conduction process. So if it is fully filled, that cannot take part in the conduction process. So what happens in the conduction process is few carriers will have to go from, in the case of insulators and semiconductors, they will have to go from valence band to the conduction band, and then they can take part in the conduction. Okay, is it clear?
Yes,
Yes,
sir.
sir.
Please. Hello.
Yes, sir. It
Yes,
is clear.
sir. It's clear.
Is it? I mean, I am not able to hear him actually.
Yes, sir. Everyone clear this point.
Yeah, so it's fine. So whereas in the case of metals, there is no question of jumping into conduction band because the conduction band and valence band are overlapping. So or very small some cases. So there are a lot of empty states available. So when you apply electric field, they can move, they can freely pick up the energy. So that is the difference between the conduction process in insulators and the metals actually. So here there is typically the conduction band will be empty and valence band will be fully filled. So then there cannot be any conduction. So anyway, we'll next slide will probably give you a better idea. And again, we need to understand the lower valence band electrons are bound electrons. They are strictly bound to the atom or the material. So there is the upper band electrons are free to move within the, of course, they cannot come out of the material, so they can move within that. So then, as I mentioned, if a sufficient energy, that is the band gap energy is given, can move from valence band to conduction band. So that means the free so that is how we are bringing in the carrier concentration. We have seen that conductivity is decided by the carrier concentration. So now when you give energy, electrons can come from valence band. So that is how you can increase the carrier concentration. The electrons need to be excited from valence band to the conduction band. So the carrier concentration can be increased by exciting electron from valence band to conduction band. Then the carrier concentration will increase, and you will see an increase in the conductivity. So then we have seen that when electrons goes from valence band to conduction band, this I will discuss probably more in detail. But right now we need to understand when electrons go from valence band to conduction band, there will be some empty space. At that empty space, the neighbor can come and occupy those empty space. So it's like a typical example one can talk of is the bubble in a water. So the bubble, you see that bubble is actually, what is a bubble? Bubble is absence of water, is air actually. So but we see that bubble movement in water. So that is what is happening is the air is moving. So that is an empty space is moving, the water is occupying that. Similarly, if within the valence band, if there are empty states are available, I should not talk of space, I should say energy states. If empty energy or vacant energy states are available, then neighboring electrons can come and occupy. Then you will see that, you will feel that that empty space have moved to that particular where the electrons were previously occupied. So that way, a different type of conduction is also possible. That is very often known as the hole conduction. So this is what is happening, that the carriers are excited and the free carriers are made available. The carrier concentration can be changed. So the conductivity can be changed by giving energy. So that is what is happening in the temperature. When you increase the temperature, some of these material, the carrier concentration can be increased, if provided you can excite them from valence band to conduction band. So different pictures are more or less the same thing, which already we have discussed. So if you have a metallic, either will have a partially, see, this is the essential difference between a metal and a semiconductor. This is at absolute 0 degree Kelvin. So a very important observation you can make is at absolute 0, insulators and semiconductors are identical. They show very low conductivity. The reason is this. In the case of metals, you have a partially filled conduction band is there even at absolute 0, because there is no gap actually, because in this diagram is slightly misleading. I'm sorry for that. So there will be a very small energy gap, or there is no gap in the case of metals. So then there will be, that means the conduction band is only partially filled. So there are carriers available for conduction. So they can contribute to the conductivity. Whereas insulators and semiconductors at 0 degree Kelvin, there is no, the carriers, the conduction band is empty, and the carriers cannot be excited from valence band to, there is no enough energy, thermal energy, even thermal energy is not there to excite the electrons from valence band to conduction band. So you have a fully filled valence band and fully empty conduction band, so no conduction. Whereas in the metals, you have a fully filled, it may be filled valence band, but you have a partially filled conduction band is there. So the conduction process is possible. So that is a difference. So you can see that insulators and semiconductors have identical behavior at 0 degree Kelvin. So now a little bit more about these metals. So there are typically you see that 3 kinds of metals depending upon their valencies. If monovalent, That means the valency is 1. So the outermost orbital might be having 1 electron. So they like typical example. They typically show very high conductivity like gold, so silver, copper. So you have so here energy is half filled. So that is not fully filled, like the case which we are showing. Then you have the magnesium, beryllium, etc. The divalent metals. There you have overlapping conduction valence bands. So they conduct even if the valence band, because it's when you're talking of the band, it is all same. That means the same kind of it can within the band the electrons can move. So there are a lot of empty states available when you are talking of the overlapping. So there can, even though it is only one band is there, the carriers can move. So this is the picture we have in the case. There is a slight difference between monovalent metals. Monovalent metals means you have a small conduction band is there. The gap between the conduction band and valence band is there, but the conduction band is partially filled, so that can take part in the conduction process. So here you have in the divalent metals like magnesium, beryllium, etc. You have an overlapping conduction and valence band. So there are empty states available within the conduction band. So essentially only one band you can say. So there are empty states available. So there will be, they can conduct. So this is a kind of two kinds of metals which we see. That is why when we talk of metals, generally we say either a very small gap or we say talk of overlapping conduction band and valence band. So this is the picture we have for the metals actually. Now coming to the semiconductors, you have this kind of thing. So we have seen that at absolute zero, or the conduction band that is 0 Kelvin, you have the fully empty conduction band and fully occupied valence band. And when you increase that room temperature, or when you increase the temperature above absolute zero, gradually electrons will pick up energy and they will move towards the conduction band. So there will be partially occupied conduction band will be there, and there will be a lot of vacant states available. So that can also take part in the conduction process, which we have seen, like the bubble in the water. So this is so diamond. What is the other name for diamond? What is diamond actually?
It is carbon.
Hello? Yeah, it's carbon actually. So you can see that there are carbon has different forms. One of the most useful materials. So in nanotechnology, you have carbon nanotubes. But much before that, and the chemistry, you have a branch of chemistry totally devoted to carbon. So it's a very versatile compound material element. So there are crystalline carbon. One is diamond, and otherwise graphite. Nowadays, you have two-dimensional material like graphene is also there. So diamond has crystalline properties. So it has the band gap of, but it is a very good insulator because the band gap is above 5. So this is again for the continuum. You can see that, and again they are all from the same group: silicon, germanium, carbon, from the same group of the periodic table. But its band gap is 5.4 electron volts or so, whereas silicon shows a band gap of 1.1, and germanium shows around 0.6 or so. And so others have higher, like gallium phosphide, gallium arsenide, etc. As of course, indium, antimonide, etc. has lower band gap than even germanium. But these are some of the semiconductors which we very often come across. So they have a different band gap. So this we can see that. So semiconductors come this, and example of insulator, we can take it as diamond can be taken as an example of an insulator with a band gap of 5.4 or so. Mind you, diamond, silicon, germanium, etc. has similar kind of crystalline structure, because there are different types of crystalline structures. So we are not going into crystallography, But if you look into the structure, the unit cell and things like that, they are so very often silicon germanium are termed as diamond-like structures, whereas the gallium arsenide we have a different kind of structure. Gallium arsenide, of course, it is not an element. It has two. It's a compound, gallium and arsenide, chemically bonded. So that is how it is formed. So the its crystalline structure is different, whereas silicon germanium has a diamond-like structure. So, but you see that the energy gap comes because of the interatomic spacing and their atomic number. So that way they are different. So this is kind of energy band picture we have for the metals and semiconductors. So this again a bit of elaboration which already we have talked of. So to conduct electricity, we need to have a band that has some filled state and some empty states that can be occupied by electrons. So the filled states of the electrons can go from the filled state. That first of all, the electron should be available, and then second thing is there should be empty states where the electrons can go and occupy, and when they increase the energy. So both these conditions are important. Conditions are very important in the conduction process. The electric conduction takes place when there are filled states, and where from there the electrons can take the energy and then go to an empty state where it can occupy. So then only the conduction can take place. So this again I have elaborated already. Metal can conduct because even at the uppermost band contains some electrons and some empty available energy states. So at 0 degree Kelvin, semiconductors behave like an insulator. So this already we have explained. So at finite temperatures, when you are at a room temperature and above, when we talk of a temperature, normally we talk of the room temperature. But above 0 degree Kelvin, this happens. But normally when we talk of material, we talk of the room temperature. Room temperature, the semiconductors have finite electric conductivity, so reasonably high conductivity. But of course, compared to the metals, it is not that high. But you can see that there is as compared to insulators, they have a good conductivity. That table you can refer back. What is the room temperature conductivity of the semiconductor, especially silicon germanium? And you can see that. So this is the band gap. We can see that. So one important thing we can see this, it is sensitive to temperature also. The band gap doesn't remain constant with temperature. So when we talk of like the case of conductivity also, we have defined it at a particular temperature. Similarly, the band gap also, but then the dependency is not that high. So very often one can neglect, but there are significant changes. You see that from 0 degree, the band gap of silicon is 1.17 electron volt, whereas the room temperature, it is 1.11. So typically we say that the band gap of silicon is 1.1 electron volt and things like that. So similarly for germanium is 0.74 and at 0 Kelvin, and then at room temperature it is around 0.66 electron volts and things like that. So the energy gap also changes with temperature. There is a decrease in the energy gap with increase in the temperature. Very often we may ignore that in our discussions, but we need to keep it in mind that it changes with temperature. Now, so this is so here one more thing I would like to mention is that we have seen that the basic conduction process in this discussion, we have seen the basic conduction process. We have not touched upon our real issue. One thing we have seen that the carrier concentration can change with the temperature. So, and the nature of variation can be different for these three kinds of materials because of the energy gap, very difference and things like that. That is one thing we have seen. Now, a little bit more about the how this energy band can be. This qualitative weight is fine, but if again, engineering is not about qualitative discussion. Engineering is all about quantitative discussion. We would like to know what is if there is a band gap. I would like to know what is the band gap. So, for example, we have seen that at 0 Kelvin it is 1.17. It's a definite number. We are not saying that there is a some band gap is there. We are saying talking in terms of definite numbers. Similarly, at the room temperature, again, we are defining. So that means, again, we are talking in terms of real numbers. Similarly, for germanium. And we cannot say just like that the germanium, the band gap is smaller than silicon. We have, again, talking in terms of definite numbers. So that means we need to have a model, and based on that, we can calculate. But that is one thing. Second thing is we can do the experimentation, and through the experiment, we can find out the band gap and band structures, etc. So a little bit about that we will discuss in the next class. And before just wind up the today's discussion, I have few questions. So we just discuss, and then this is happen to be the weekend. So I may give you some assignment for the weekend. You can carry out it in between. Of course, you don't have to finish it by Monday, but before next Saturday, you should try to work on them. So that will elaborate, and you can watch that video which I mentioned. So let me pick up the questions first. So some of the things we have already mentioned in this discussion. The essential difference between different states of matter that we have discussed already, because we have seen that interatomic distance is the different states of matter. And there is a fourth state of matter. What is the fourth state of matter? So let me start. If I remember some of the names, let me see how good I am with the names. So I will ask the names, so they should answer. Is it okay? Hello?
Yes,
Hello?
sir. Yes.
Hello?
Yes, sir.
Yeah. So I'll be calling the names. They will answer the questions. Okay? Fine?
Yes, sir.
Let me see.
Sir,
What are there? Yeah. On the top, I'm seeing Meenakshi. So let me ask you, what is the fourth state of matter? You have seen three states of matter. What is the fourth state of matter?
So solid, liquid, gas,
Yeah,
and
that is
plasma.
three states. What is the fourth?
Plasma.
Yeah. And where is it
Plasma.
found in nature?
Fi- Sir,
Pardon?
nature, sir, basically.
Pardon? Sound little loud. Where is it found? Yes.
So, physics part found.
Yes, I can't hear you.
So it's a part of
Part
physics,
of?
basically. All
Part
are
of?
the all are the part of the physics.
See, actually, we need to understand this
Uh-huh.
states of matter is decided by the energy. So, for
Sorry, sir.
example, if you provide
Yes, sir.
energy, solid will become liquid. If you
Yes, yes,
give
yes.
further energy, liquid will become gas. And
Yes,
if
yes, yes.
you
Sorry.
again further give you energy,
These are one
it's all
confusion.
the matter play of energy.
Yes,
The
right,
electrons
right.
will be coming out of plasma state. Plasma state is a mixture
Plasma.
of positive and negative charges. That is all.
Yes, yes.
So it's energy. So such high energy exists in stars.
Sun.
So normally stars, for example, if you go to sun and the things like that, they're naturally. Otherwise, you can create plasma within the lab conditions. That is there, but one can. There is so it's a matter of energy. So generally in stars, the matter may exist in the form of plasma.
Sir,
Yeah.
what is the sir? What is plasma TV? मतलब what?
Actually, there we will be using plasma. You have the like ions are and ion and the electron. Plasma means basically a mixture of positive and negative charges. That is what. Unlike your, because they can be electrically charged. So unlike your normal atom, because there is a neutrality. So that is what. So am I audible to all of you? or only Nishant, Prashant is facing some issues?
Yes, sir,
Yeah,
you are
yeah.
audible.
So that means it is Prashant's issue. Yeah, so that is there again. We can use it for display purpose. So that is where the plasma tip. Yeah. So that is artificially created. That is not natural because you are giving energy and ionizing the gas or something. That is what. Yeah. And now the second question: can I control the band gap of the material? Let me ask Nithi. Can I control the band gap of the material?
Um, no, sir.
So so this is where so the naturally occurring band gap you cannot play, but today we have the capability because we need to understand that is where this fundamental understanding helps us. We have seen that the band gap is decided by the atom, the atomic number of the material, and the interatomic spacing. If I can play with that, see, if I can play with these two things, one is the atomic number and the interatomic spacing, I can change the band gap. So if I put a neighbor, that is what I've been discussing. Heterostructure is an example. You have silicon, and even if I can do the play with the silicon atom interatomic spacing, there also I can change the band structure. In principle, it is possible, and it is done. But of course, it is not changing the interatomic spacing of silicon. You put a different neighbor close to silicon. So that way it is done. Yeah.
Okay,
So
sir.
it is possible. Yeah. You want to say something?
No, sir. I understood. Okay, sir.
Yeah. Yeah. Because nanotechnology is all about that. That is why. So, do you suggest any fabrication technique which can be used to create the structure? So that is. Let me ask Prashant. Can you suggest a way to get? Said that we can create heterostructures. That means the neighbor of silicon is a different material. So you have already studied some technique of fabrication. So which fabrication technique can be used for creating or playing with the band structure? Yeah, Prashant. So Prashant is not able to hear me probably. Yes.
Sir, pardon,
Yeah.
sir.
So what fabrication technique can be used to change the band structure or heterostructures? What is the technique used?
Doping,
Pardon?
doping.
No, it's actually you might have heard of. I don't know. I think it is there in the syllabus in the first year. That is molecular beam epitaxy (MBE).
Yes, sir. Yes, sir.
Molecular beam epitaxy. Have you heard of that?
Yes, sir.
So actually, if you have not heard, then you will be coming across that. Molecular beam epitaxy can be used because molecule by molecule you can deposit. So you can mix silicon, then along with that gallium arsenide, or I mean, normally used with the compound semiconductors. You can make gallium arsenide, gallium aluminum arsenide, etc., using molecular beam epitaxy. So there we can get this kind of band gap engineering is possible with uh, with that kind of fabrication technique. Now another question comes: can liquid state can have crystallinity? See, we talked of solids, and we have seen that solid states only give you crystalline structure. Now, my question is again going back to
Yes, sir.
uh,
LCD.
yeah, very good. You are jumping the gun anyway. So actually, LCD they show some typical properties of liquid, but they show some properties of the liquid in the sense periodicity. Periodicity is the important property of crystalline material. So liquid crystals very often used in many of the displays, etc. The liquid crystal is a classic example where liquids also show some crystal, but otherwise most of the liquids are doesn't show any, because that goes against our definition of the crystal, because crystals means there is a periodicity and atoms remain there. Whereas in liquid, it takes the shape of the container. So that way, but a certain class of liquid, because they show some properties of the liquid and some properties of the crystal, so especially the periodicity. So you have liquid crystals. So probably you might be studying it in your optoelectronics paper more about it. So I'm not going into the details, but you should remember that liquid crystals are there, but they are very limited category of liquids only, not all the liquid. Yeah. Now on to the next one. Now, can you suggest a way to find out okay, first let me ask you, do you expect, see, we have seen that diamond, silicon, germanium are the same kind of band structure. Do you expect their band gap also to be same? Of course, you know that it is not same, but then why it is different? Yeah, Prashant. Oh, Sudha is there. If she can hear me. Hello. Sudha, can you hear me?
Yes, sir.
Yeah, my question is silicon, germanium, and diamond. They are of the same periodic table. Is their band structure the same, and the band gap also same, or is there any difference?
So different.
Why they are different? And what is the similarity? Is there any similarity at all, or only everything is different?
So in band gap, diamond as an insulator, we use diamond as an insulator, so its band gap is more.
Yeah.
But in silicon, band gap is less.
Yeah.
Yes,
so what is there anything similar in these three?
Don't know, sir.
See, actually, as I mentioned, they have their band structure is identical, whereas the band gap is different. Actually, the nature of the structure. If you look into the band structure, they are, because they are the periodicity. Because all of them have the diamond structure, so there will be some similarities in the band structure, whereas the band gap is different, because we have seen that the band gap of diamond is very high, silicon comes second, and the germanium is very small. Because basically the atomic number and the interatomic distance is different. Again, one can go from that with that argument that their interatomic distance and atomic number are different. So naturally, their band gap will be different. But their crystalline structure is identical, so the band structure is similar. So that is one thing. Now, can you suggest a way of finding the band gap? So who will answer that? Okay, Niti, let me come back to Niti. You got the question. Can you can you suggest a way of finding the experimentally? Theoretically, I have not touched. We will come to discuss about it in the next lecture briefly. Is there any experimental way of finding out the energy gap of material?
Sir, we can provide energy to see when it is conducting, so that energy
How it is
will.
possible? Practical way, you can tell me a practical. Okay, that is true. Yeah.
Um,
Yes.
We can throw
Yeah.
of particular wavelength and then see their conductivity.
Yeah, that is actually there are one or two ways, which one already you have done, and other one is using the optical. So method, you have electromagnetic radiation, and corresponding to what, because corresponding to band gap, the photon absorption will be peaking. So from that wavelength, and can make out the band gap. Then other experiment you have done, conductivity measurement, because again there is a relationship between the conductivity and the energy gap, which you do. I mean, I expected that. Okay, probably you may in the second semester because of the COVID. Because otherwise, you were supposed to do an experiment in band gap measurement in the second semester. There we make the measure the conductivity and find out the band gap. So there you are the relationship between the conductivity and energy gap is used to find out the. So these are the techniques one can use, either the conductivity measurement or optical method. You can change the wavelength of the photons, and at a particular wavelength, you will be seeing a sharp increase in the absorption. So from the absorption, that particular wavelength, you can find out that the wavelength, the band gap of the material. So this is the question I wanted to just to elaborate on the points. So now these are the some of the things. So this anyway, you don't have to note down. The only thing is you can just quickly read it. And are you able to read? Oh, sorry, you are not able to read, no?
No, sir, you are not presenting.
Yeah, I will present it. So you just quickly read if you need any clarification, because otherwise the slides will be available. So you can copy it from there, but I will just quickly present it. And then you can note down and later on you can note down. I can read it. Yeah, are you able to see?
Yes, sir.
Yeah, actually, I just wanted to see your engineering skills. So simple. We in the very first lecture, I said engineering is all about converting physical laws into useful product. So you find at least minimum three engineering application of Ohm's law. You are always welcome to give more applications, but it should be different. So you should do it independently. So just to test your engineering skill. So you got the question? You understood the question?
Yes, sir.
Yeah. Second one. Yeah, Prashant wanted to ask something.
No, sir, no.
Yeah. Second one is explain the importance of abstraction in engineering a product. We talked of again based on my first lecture. So for example, you may use IV characteristics as an abstraction, or you need not be limited to that. But then, what is the importance of abstraction in engineering a product? That means designing a product. What is the importance of abstraction? So I just wanted to know how much you understood about that, so you can again give some examples. And then the third one is example. Can you explain the role of mathematics in engineering? Again with an example. So there is one more thing. This is a numerical. This is just to we are able to appreciate the microelectronics. So instead of the question is broadly, I'll tell you the question is instead of integrated circuits, if you are using 100 million transistors for making a microprocessor, so what will be the consequences? You got the question? Hello?
Yes, sir. Yes.
Yeah. So you just do. Pardon?
Can you explain the last one? 100 million, some.
Yeah, 100 million. 100. See the question. The question in the question, all those details are given. What all we are talking about? See, actually, we are talking about 100 million transistors. The chip area is given. Then the chip thickness is given. Then dimension of a single transistor is given. So just to see this, with this you will be able to appreciate the importance of microelectronics in the context of microprocessors, etc. That is the idea. Nothing is a high school calculation only, so don't worry. But try to do that. Okay.
Okay, sir.
I think I'll stop it here today. So all these things will be available online, so you can take advantage of that. The slides will be available, so you can note down the questions. So, but I expect that you will try to work it out and file it by Saturday. Okay.
Okay, sir.
Okay. Bye.
Okay,
Thank you,
sir.
sir.
Yeah, bye.
Thank you, sir.